Hi there, guys. We're going to try and do 1F now. Remember, 1E was about proof and direct proof, just saying, here's a statement, let's do some mathematics to prove that something else is true. That's just a direct, straightforward proof. In 1F, we're going to build up to proof by contradiction, and we're going to do that by discussing contrapositives, what the contrapositive is, and then what a proof by contradiction is. And then later on, a kind of easier thing is, just not to get confused, is just proving something is not true by coming up with counterexamples. That'd be a little thing that we're going to tag on to the end of this as well. Okay, so I'm about to do example 12 in a moment, so the investigation 12, which is reasonable. Okay, you should be able to do this on your own, but I'll lead it through because it's perhaps not totally obvious. But before that, we're just going to deal with a kind of logical real life statement to give you an idea of what the contrapositive is. So I just stole this from somewhere online. Find out where I did steal it from. Here we go. I just put in proof by contrapositive. Okay, it came up with this example here. So the statement reads like this. It says, if Harry had opened the right book, then Harry would have learned about gillyweed. Okay, so that's saying, if you like, I don't know, let's call it book leads to, implies that Harry has learned about gillyweed. So B can stand for Harry has opened the right book, and G can stand for Harry has learned about gillyweed. So one implies the other. Okay, so B implies G. Now, the contrapositive is an equivalent statement. So the contrapositive says, if Harry didn't learn about gillyweed, so we can say, if, put this kind of curly thing, sometimes you see logical symmetry, they write kind of like this, but we're going to just write it like a sort of not G there, this curly line. Okay, so not G. So if Harry didn't learn about gillyweed, that implies that Harry didn't open the right book. Okay, so he didn't open the right book. And so that's logically, that sort of common sense idea you can get your head around. If Harry didn't learn about gillyweed, then he can't have opened the right book. And in fact, this statement here, this is your contrapositive. So it's the reverse of the statement above, but with both of those things being negative. So the implication sign goes in the other direction, but they're both negative. Now, these two things are logically equivalent. Now, you can obviously muddy the water here by starting to say, well, you know, perhaps Harry does know about gillyweed, but perhaps he didn't read the right book, but perhaps his friend told him about gillyweed, so he knows about gillyweed because he learned it somewhere else. But that would be a different statement. It is true to say that if you started the other way round, so if you said, if Harry didn't learn about gillyweed, then Harry didn't open the right book, then it's true to say, contrapositive of the contrapositive is the original statement, then it's true to say that if Harry had have opened the right book, then he would have learnt about gillyweed. Okay, I'm kind of whittering on about this, but this is quite, these are difficult logical concepts to get your head around. But, you know, we need to reduce this in terms of mathematics to understand that if A implies B, then if you can show instead, because maybe you can't show something directly, come up with a direct proof through a set of steps here, but if you can say, well, let's start with not A and show that start with not B and show that not A is true, then that's equivalent to saying that A does imply B. Okay, and this is called your contrapositive. Okay, now the process of saying instead of doing this direct proof, we do this proof here by using the contrapositive, that's also a proof by contradiction, by using the contrapositive. So I know where it says here, they say this is called a proof by contrapositive. Yes, it's a proof by using the contrapositive, but it's called a proof by contradiction normally. Okay, and that's what we'll be calling it in mathematics. But this is the contrapositive. Okay, right. So let's try and take the example we come up with. Let's take investigation 12 to kind of work that one through and see what they're talking about. Okay, so here's investigation 12. And so this is for 1F. And it leads you through two proofs here, a direct proof and a proof by contradiction, essentially. So the first one here, the first little statement says, write a direct proof of this statement. What is the statement? It says, if n is an integer, and if 5n plus 2 is even, then n is even. So we're essentially saying 5n plus 2 being even, if this is even, then that implies that n is even. Okay, so we're going to do a direct proof on this one. And for a direct proof, we're going to start by saying 5n plus 2 must be equal to 2k, where k is some integer. Okay, it's 2k is going to be an even number if k is any integer. Okay, well, I guess there's different ways of doing this, and I'm going to do it by taking 2 off both sides and then realizing that that's also going to give us an even number, because if we take 2 off an even number or add 2 to an even number, we still have an even number. We just have a different even number. So in this case, I'm going to call that 2m. Okay, so now I'm going to say, well, m belongs to my integers. Now, it might be at this stage that you say, well, look, if we've got a number in the 5 times table is equal to a number in the 2 times table, we can see that only even multiples of 5 are going to give us a number in the 2 times table. So you might think, well, 1 is not in the 1 times 5 doesn't give us an even number, but 2 times 5 does, and 4 times 5 does, and 6 times 5 does, and so on. And this is, once you get down to a really basic statement, you can just state this is kind of obvious. Okay, these are the building blocks that we understand to be true already. Okay, but I'm going to take this a little further in a sort of more formally here, and I'm just going to say, actually I could call this something. I'll say let, and in this case, let's just say let p is equal to 5n. That's equal to 5m. And that implies, so we're saying that p is both a multiple of 5 and it's a multiple of 2. So within the prime factorization of p, you then must have a 5 and a 2 timesing by some other integer. It might be 1, might be whatever, just some other integer, okay? Where L belongs to the integers as well. Okay, so now I've got the fact that 5n, okay, which is here, is now equal to p. If p is equal to this thing over here, so 5n is equal to 5 times 2 times L. And since we can now say that that's equal to 2 lots of 5L, well, we can then cancel the 5 from all of those things, and we can say n is equal to 2L, therefore n is even. Okay, now I don't think the book goes through that many steps, but I'm just trying to be as rigorous as possible there. Okay, and I'm probably missing a few implication signs. The implication signs are linking up our lines of working out. This is basically like this line implies that this line is true. That's what this arrow is doing here. Now, by the way, in mathematics, if you use an arrow with just a single arrow, not sort of a double stroke arrow there, then that means tends towards in mathematics. So we don't use a single arrow. We have to use this implication symbol to link our lines together. Now, in an exam situation, if you forget some of your implication signs, they're going to be relatively generous. I think they would accept my proof here, for example. But I think probably I could have gone from this line down to here by saying this implies this, and this implies this as well. Okay, so we're just linking everything up logically. And at this statement here, I mean, it was good that I was saying to the examiner, instead of implying, I said, let this be true. So this line here wasn't implying this line. I just came up with another definition here. And so that's why it's kind of useful to show what the examiner that you understand the steps. Are you implying something? Are you defining something? So we're trying to show clearly mathematically how this is all set up. Right, I've now done this part. Okay, so I've done one. I've done the direct proof n is even. Okay, that is done. Okay, but that's the direct proof, and that's what we did last time round, and you should be able to prove that already, although that's relatively tricky, I think. So for question 2, it says, now assume that n is an odd number. So we're going to go backwards on this one, and we're going to show that the contrapositive is true. Okay, so what we've done so far is we've shown A implies B, the direct proof. Now what we're going to do is show that not B implies not A, and that's equivalent to the top statement. So that would imply that the original statement is true if we can show this. Okay, and now that gets quite difficult to think about, but again, either remember this or go back to that original statement which we found about Harry and his books. If you remember that, then you remember the implication statements as well. Okay, so for part 2, it says, now assume that n is odd. So we're assuming this. We're going backwards. So if n is odd, then we can write down that n is 2k plus 1, where k is an integer. So we're assuming that n is odd. We've done that. And rewrite this expression to reflect this. So we're going backwards. We're going to assume this is odd, and we're hopefully going to get out that 5n plus 2 is not even. Okay, right. So in fact, this one is a little bit easier. So I probably need to write down this belongs to Z, and I probably should say to the examiner, assume that this is true, that n is an odd number. Oh, by the way, previously I was using -1 there, but you can use +1 or -1. It doesn't really matter, especially as we're thinking about integers. We're not necessarily talking about natural numbers. So right. So it doesn't necessarily have to start with 1. That's what I'm talking about. Okay, so assume this is true. And so we're going to then put that into here. So we're going to do 5 times 2k plus 1, and then plus 2. And if you do that, so this thing implies, so this thing over here, should link this up, implies this thing here, which of course gives us 10k plus 3. And then obviously that's an odd number, because you can then take out, let's say 10k, let's make it really explicit, plus 1, and then you can say that's equal to 2 lots of 5k plus 1 plus 1, and then you can say therefore that is an odd number. Okay, and it's an odd number because, and you can continue if you want to, you can say because 5k plus 1 belongs to our integers. Okay, so an integer times by 2 is even, and then plus 1 gives us an odd number. Okay, that's done. So what we've done is shown that an odd number implies that 5n plus 2 is also odd. So we've shown the contrapositive, and the contrapositive is enough then to say that this original statement is true, A implies B. So we found a different way of proving the original statement. Okay, that's pretty hard to get your head around, I think. That might be worth listening to a second time. But let's have a look in the book. Let's just see what they say, because there's a little hint here as well. And then we're going to move on to a proof by contradiction, which is essentially the same thing, but we're going to take the absolute classic proof by contradiction. We're going to take example 35, the show that the square root of 2 is irrational. Okay, but let's just have a little look at what the book says. So in the little hint box that they've got here, they say a proof by contradiction is built on the logical reasoning that if a proposition is true, then its contrapositive is also true. That is, if in a statement A implies B, then it is also true that if B is not true, then it implies that A is not true. And those are two equivalent statements. Okay. Now, I'm going to skip this little investigation here, but again, this is another nice investigation. This is a classic one as well. I'm not going to do that right now. They talk about the steps for a proof by contradiction, and I'm not going to go through this box at the moment, but I'll come back to this once you've seen one of these proofs, because the proof is relatively straightforward, and the steps, learning the steps is kind of tricky if you don't have an example to hang those steps off. So let's go to the example now. So we're going to go to example 35. Okay, what I was about to say before I rudely cut myself off was that example 35 is the classic interview question for a maths teacher. So if you're employing a maths teacher, they should be able to do this. I'm not saying they can all do it on the spot, but I've known this to be asked in an interview before. Okay, let's get rid of me. And so it says, show that the square root of 2 is irrational. Okay, well, this is actually a little bit difficult to set up as A implies B. So what we're trying to do is this proof by contradiction, of course, by coming up with not B implies not A. But I guess it's less obvious here to see what A and B are. But I suppose that we're really saying the square root of 2 leads to it being irrational. And what we're trying to prove is that, or what we're going to attempt to prove is that if it is rational, if that's our assumption, then we should find out that it can't be the square root of 2. Okay, so I think that's the format which we're going to use, but this is perhaps a little less obvious in this situation to see how it is, but I think the proof is relatively obvious as we go through. So we're going to use a proof by contradiction. So we're going to assume the opposite and end up with this not possible, with us not being able to get out the square root of 2. So we're going to assume that the square root of 2 is rational. Rational means can be written as a fraction of 2 integers. So where A and B are 2 integers here. And we also need to state that A and B are in their lowest form. So this is in a cancelled form. So where A and B don't share any factors. Okay? Or that they're co-prime is another way of saying it. Okay, so A and B don't share any factors then. We need this little bit here, and that's actually what I just missed off why I'm redoing this video, because I just missed that and then realized I missed it. Okay, now if you don't know what a rational or an irrational number is, of course you can Google these things. And when I just Googled types of number, I came up with this one. Just open this as a picture, and you can see here's a sort of fullish number system. Perhaps complex numbers are missing from around the outside. In this example, they've included 0 as a natural number, which we've spoken about before is debatable. Then we extend to our negative numbers, and we get integers. Then we extend to our fractions. And of course, fractions do include our integers as well, because obviously 2 can be written as a fraction, 2 over 1. But then we get our rational numbers, which include all integers, but then are essentially fractions, positive and negative fractions. And then you're aware of numbers which are beyond that. So you're aware of things like the square root of 2 and pi and e. And those are the real numbers. And the real numbers are themselves split up into algebraic real numbers and transcendental real numbers. And you don't really need to know that at the moment, but algebraic real numbers are solutions to polynomials. So things like solutions to quadratics or cubics would give you real algebraic numbers, but you wouldn't get out pi or e from polynomials set up with integer coefficients. Okay, so a little diversion there. Okay, so show that the square root of 2 is irrational. So we've assumed to start off with that it is rational. The square root of 2 is equal to a over b. Now we're going to take some logical steps here. Probably should say to the examiner as well, so that we should assume this. And I guess it's logical after this to say, well, that implies, what could we do to both sides? Well, we could square both sides. So equals to 2. So 2 equals a squared over b squared. And of course, we can rearrange that and we can get out 2b squared equals a squared, which implies that a squared is even. You can write a bit more there if you wanted to. We understand that b squared is an integer, so when we double it, we get an even number, whatever integer that is. So a squared is even, and that implies that a is even. Okay, now again, that's a statement which could be proved, but I think it's sufficient here to get away with just stating that. That's kind of obvious, but you could prove that using a direct proof. But that essentially comes from the idea that if you have an odd times an odd, that will give you an odd answer. And if you have an even times by an even, gives you even answer. And that idea is used quite a lot. And you can assume that that's true. And so we've assumed that this is true here essentially because we've got even times even gives us an even number. Okay, so if a times a gives us a squared, so if it works either way. So if we've got an even number, it must have come from timesing two even numbers together. Okay, let's take all of that stuff back. Okay, so that implies that a is even. Okay, in which case we can write a. So we can say let a equal to, I don't know, let's call it 2k, where, so I'm going to have to write this over here, comma, say where k belongs to our integers. Okay, now we can put that back into our statement here. So that implies that we now have 2b squared is equal to, and I'm going to put 2k back in for a because we know now that a is even. Okay, and now we're getting out 4k squared is equal to 2b squared. And of course, b squared is equal to 2k squared. Okay, I wonder if you notice something now. Okay, so here we said this implies that a squared is even. Okay, well, this now implies that b squared is even. And which implies that b is even. Okay, but we said that a and b are co-prime. We said that they don't share any factors at the start. That was our setting up of this, our fraction, our rational number in its simplest terms, as all fractions can be simplified, cancelled to their simplest terms. We set it up as a fraction in its simplest terms, and we said that a and b don't share any factors, but now we're saying that a is even, and that b is even. So therefore, they do share common factors. So in assuming that the square root of 2 is rational, we've shown that there's a contradiction in the original statement. In assuming that it's rational, we've then taken this further and ended up with saying, well, actually A and B now share a factor, which is contradicting the original statement. Okay, let's just get rid of that for a second. And so let's just go back to that original statement to show that we've used this contrapositive essentially. So we've now gone A implies B would have been square root of 2 implies it's irrational. But what we're trying to show, what we did show, was that if we assume it's rational, then we can't get the square root of 2 because of the way we set it up, because of the fact that when we set up our A over B, they ended up sharing a factor. They were both even, and therefore that contradicted the original statement of setting up the square root of 2 as a rational number in its lowest terms. Okay, A and B there, I'm also using as A and B there as well. So we've shown this. So this is what we've proved. Therefore, this is true as well. Okay, so the proof is now done. Okay, let's just have a look at what, I mean, it's worth having a look at the version in the book as well. And you can see that they've followed the same steps as me. Just at the end, let's just see what they've written at the end. Here we go. They said, but it was assumed that M and N, I used A and B, have no common factors, and now you have found that they have a common factor of 2. Hence, you cannot find M, N belonging to Z that have no common factors to make the square root of 2 equal to a rational number. Okay, so there's a little statement which is required on the end to show that you've understood what you've done. Oh, okay, right. Let's go now to example 34. We'll do 34, 36, 37, and some counterexamples in 38 as well. So to 34, more proofs by contradiction. Let's just fill these ones here. So we're actually going backwards a little bit here. Oh, and I did say I was going to have a look at the way in which they set these things up. So in the box in the book said, when setting out a proof by contradiction, you follow the following steps. You identified what is being implied by the statement. You assume that the implication is false. You use axioms, etc., theorems, etc., to arrive at a contradiction, and this proves that the original statement must be true. Okay, right. And also there's a little talk about, just underneath here, this idea of reductio ad absurdum, reduced to absurdity, which is an idea first proposed by the Greek philosopher Aristotle, or at least as far as we know. That's kind of interesting. If you want to read up on that, you can. I'm not going to go any further with that just at the moment. You don't need to say this is a reductio ad absurdum. Okay, you just need to understand that what we're doing here is a proof by contradiction, and that the contrapositive is the opposite of the original implication, with both things being negated or being negative. Okay, right, example 34 then, let's crack on. So proof by contradiction. If the integer n is odd, then n squared is also odd. Okay, so let's write it as a logical statement then. We've got n being odd implies that n squared is also odd. Now, of course, they've told us to use proof by contradiction, so they want us to use the assumption that if n squared is even, that implies that n is even. Okay, so this is what we're trying to show, and that will also show the original statement is true. So if n squared is even, and this is a really quick proof here, we've got assume that n squared is even, so that implies that n squared can be written as 2k. Just to make it more explicit, n times n is equal to 2k. And then they're saying we're kind of allowed to just say at this point that n must be even. N is even. And that's allowed. This is kind of a basic property which is allowed. And that's what the book says. So it says, but this cannot be true. Let's have a little look at this a bit after 2k. It says, but this cannot be true if n is odd, as you know that the product of two odd numbers is also odd. In other words, n must be even. Okay. I mean, if you want, you can come up with a little proof. I mean, essentially what we're using is that even times an even gives you an even number, and an odd number times an odd number, which is what we talked about before, gives you an odd number. And you can show that those things are true as well by setting up an even number as 2k or an odd number as 2k minus 1. But we're ignoring here the condition that we have an even times an odd, of course, because we know that the two numbers are the same. Okay, so if we have an even number, it must have come from an even times an even, because the only other option is to have an odd number coming from an odd times an odd. However, I'm overthinking that a little bit there. The book just allows us to state that n must be even. this is a fact that we can use. Okay, now if n is even, therefore, hence, we've shown the contrapositive is true, hence this original statement must be true. Okay, all right, let's get rid of that. Okay, for part B, it says if n squared is even, so we've got n squared is even, then n is also even. And n is even. Okay, well, that's what we've just shown, but they want to use proof by contradiction in this case, and the proof by contradiction would be to say, assume that n is odd, therefore n squared is going to be odd. Okay, that's what we're working towards there. So we're going to do assume that n is odd. Okay, so that implies, all right, and just slowing down a little here, struggling to keep up. So that implies that we have n equals 2k minus 1, and then n squared must be this thing squared, and then we've got 4k squared minus 4k plus 1. That's our n squared. And then if we take out a factor of 2 from the original 2 here, the first two terms, we've got 2k plus 1. And now we can see that we've got an even number plus 1 gives us an odd number. And we should really have a statement at the end there to say, therefore, n squared is odd. You might want to just write because this is even, and even plus 1 gives us an odd number. Okay, so we've proved this, and that means that the original statement is true as well. Okay, again, let's just check what the book does. So they've got a little statement on the end. Interestingly, they write an odd number as 2k plus or minus 1, but you can use plus 1 or minus 1, it doesn't matter. Did I forget to write k belongs to my integers? Yes, I did. So I forgot to write, I should write that down, otherwise I might lose a mark. So k belongs to the integers here, right, just after setting up this definition. Okay, right, so that's example 34. Let's crack on to the next. We've done 35, so we're going to do 36. Take this one. Okay, so for 36, I was struggling really to get my head around what is A implies B here in the first case. But I guess I'm pretty much overthinking this again. So this one says, prove that there is no x belonging to R such that this equation has a solution. Okay, so it's basically saying this equation doesn't have any real solutions. So it's quite difficult to think in this case, what is A implies B? And I tried to write down some of these in thinking this one through before I went through this one. And I mean, is it the equation implies that there's no solution or no real solution? And that if we assume there's a solution, we should find that the equation doesn't work. Doesn't work. Okay. I think that's kind of less obvious. I think basically in this question, I think it's just more obvious to see that let's assume that there is an x which works here. Okay, and let's call that a particular value. And let's show that that particular value leads to an equation which can't possibly have any solutions, any real solutions. Okay, so I think this one's just a little bit, dare I say, a bit kind of obvious. So prove that there is no example that works. Well, let's assume that there is an example that works and show that that leads to a contradiction, that there can't be an example that works. Okay, so assume, now I could say assume that there is an x that belongs to R which works, it belongs to our real numbers which works, but because all we need is one solution, let's assume that there is an x belonging to R which makes this equation work. Assume that there is an A that belongs to this such that such that 1 over x minus 2 has a solution of has a real solution. Okay, I'm kind of overthinking this one a little bit again, and we're going to put in a essentially into here and try and solve it. So we've got 1 over a minus 2 equals, implies, this original statement implies this minus the a. Let's take this to the other side. You'll see that you've got a quadratic. You've got 1 minus a times by a minus 2 there. And then when you try and solve that quadratic, I'm just going to skip some steps here, okay, because they're pretty easy for you to do. You end up with a squared minus 3a plus 3 equal to 0. And that implies, using the quadratic formula, that you get out a is equal to 3 plus or minus 9 minus 4 times 3 divided by 2 times your coefficient of a squared, which is 2. Okay, so we're just using the quadratic formula with the coefficients 1, minus 3, and 3. I know that's kind of confusing in terms of when we normally use the quadratic formula, we have a lots of x squared b plus c. But in this case, it's all in terms of a. It should have chosen a different letter. Anyway, this doesn't have any solutions because if you look at the discriminant, you see that that is negative. We have 9 take away 12 there, gives us a square root of a negative number, which means that this can't have any real solutions because you can't take the square root of a negative number. Okay, so there needs to be a little statement at the end there. Sorry, I'm running out of space and I'm feeling like I need to hurry up a little bit on this one. So let's just see what they've said. So there we go. They've stated at the end that this does not belong to our real numbers. So we were looking for a solution that worked, and we ended up finding that that solution doesn't work. It doesn't give us a real solution. It gives us a complex solution, but not a real solution. Okay, I think I'm overdoing that one really. So example 37, this. Okay, now this is the last of the proofs by contradiction here. You might want to have a go at this one yourself, but this one requires a fair bit of creativity in order to sort this out. So it says prove that if m and n belong to your integers, then m squared minus 4n minus 7 doesn't equal to 0. Okay, so what are we going to show? Well, this is saying m and n belong to your integers. That implies that m squared minus 4n minus 7 doesn't equal to 0. So we're going to switch that around. We're going to say the contrapositive in this case is m squared minus 4n minus 7 equaling to 0. So if we assume that's true, we should find out that m and n do not belong to the integers. Okay, so where do we take it from here? So we've got this statement, we've got m's and n's there, so it's not like your regular quadratic solve. But we're going to assume, let's just start off with the obvious line in the proof. Let's assume that m squared minus 4n minus 7 is equal to 0. And then I think we've got to play around with this a little bit. So this implies, what can we say about m squared? Let's take the other stuff to the other side. We've got 4n minus 7. Now you can see that 4n minus 7 is an odd number. So this implies that m is odd. Remember, that was one of the facts that we could use before, that if we have odd times odd equals odd, then m squared, if m squared is odd, then it must have come from squaring an odd number. I mean, you can check that, of course, by doing 1 squared. This isn't a proof, by the way, it's just checking, just to, sorry, what am I, 2 squared, 3 squared, 4 squared, and so on. I mean, these are giving you odd numbers, and these are giving you even numbers. So if you get an odd number, it must have come from an odd number squared. Now we can just use that. I think in the book they say, well, let's just take this a bit further to show that it's odd. I mean, I think you could do that by saying, let's steal a -6 from there. You could set that up as 2 lots of 2n minus 3 minus 1. So we can show that that's odd. If m squared is odd, then we've got m is odd there as well. Okay. So now if m is odd, we can let m equal to 2k minus 1. Okay, now we can put that back in up here into the original equation, into our original assumption. That implies that we're getting out 2k minus 1 squared minus 4n minus 7 is equal to 0. Okay, well, if we multiply that out and take, well, let's actually do that. If we multiply this thing out, we're going to get 4k squared minus 4k plus 1 minus 4n minus 7 is 0. And then now we've got 4k squared minus 4k, just simplify it, not doing anything clever here. And then I can see at this stage, I'm not really sure where to go, to be honest, but I can see that everything has a factor of 2 there. So my next line, I would divide everything by 2. So 2k squared minus 2k minus 2n minus 6 equals to 0. And I'm just going to take the minus 6, which, by the way, should have been minus 3 because I'm dividing everything by 2. Shows you that I shouldn't skip steps. Take the minus 3 to the other side to get plus 3. Okay, I'm still just playing around with this. I'm not quite sure where this is going, but I notice that I have all 2's on one side and I have a 3 on the other side. So I now see that we've got, I factorize out that 2k minus n is equal to 3. And now I end up with an even number, okay, because we know that this is just an integer, equaling to an odd number. So we've ended up with a contradiction here. So we've assumed that this is true, and we've assumed that it's true, and we've assumed as well that m and n are integers, and that k was an integer. Perhaps I should have stated that at the start here, right at the beginning. I should have said m and n are integers. And what we've ended up with is a contradiction. So that means to say that m and n can't be integers. So m and n cannot be integers in this case. Because if they were integers, we'd end up with an even equals to an odd. Okay, so what have we done? We've shown the contrapositive. We started with m squared minus 4n minus 7 is equal to 0, and we ended up saying, well, m and n can't be integers. Well, that's the same as saying the original statement, and the original statement being that if m and n are integers, it implies that this thing is not equal to 0. Oh, that was quite tricky, I think. And there's a lot of just playing around in this question to see where you can get with the algebra. And some of those steps might not be obvious to you. And in an exam situation, that's really quite hard to get. But hopefully after playing around with it for a bit, you'll get down to this idea that you have an even equaling to an odd, which therefore means that k and n can't be integers, which leads to m and n can't be integers as well. So when I stated that m and n are not integers, I guess we're really saying that k and n are not integers. But of course, that also implies that m is not an integer because we have m being based on k. Okay, so maybe we need another step in there as well. Okay, you might need to go through that a couple of times in order to figure out how that worked. But again, it comes down to we set up A implies B, and if they're asking for us to prove something by contradiction, but which, by the way, they didn't actually ask for here, but it's what we're having to do, then we can set up the contrapositive and we can try and show that the contrapositive is true in order to end up with the original statement being true. Gosh, right, okay. So this is tricky, right? You can see that I've done a lot of chatting here, and it is tricky to describe, and these are very tricky logical arguments that we're creating here in order to satisfy our examiner in each of the cases. Okay, now you'll be happy to note that the last part is pretty easy and pretty obvious. Okay, so we're talking about counterexamples now, and in terms of counterexamples, let's just check that out again. It says a counterexample or a counterclaim, I'm going to call them counterexamples, is an acceptable proof of the fact that a given statement is false. Now, I just checked one of these out earlier, and this was the one which I had. This was the one which I found. Okay, so here we go. It says here in these quotes, it says, you can never really prove the proposition that all swans are white, even if you have only seen white swans in your entire life. So going through many examples doesn't prove that there are exclusively white swans. It may be that you just haven't seen a different colored swan. But you can certainly disprove the statement or the proposition, which, by the way, they've called proportion here. They shouldn't have said that. They mean proposition. You can certainly disprove the proposition by seeing a single black swan. So we just need one counterexample to disprove the original statement that all swans are white. We just need to see a black swan, and then we've disproved this original statement. Okay, so that's what we're up to in the last part here. We're talking about counterexamples, and this is pretty easy. You can imagine this would be a 1, maybe possibly a 2-mark question just at the start of a question. Okay, so show by counterexample that the following statements are not true. It says if n belongs to our integers and n squared is divisible by 4, then n squared is divisible, then n is divisible by 4. Okay, so let's just think of some examples here. So it says if n squared is divisible by 4. Well, let's just think about our square numbers. Again, here we don't need to come up with this in algebra. We just need an example. So our square numbers are 1, 4, 9, 16, 25, 36, and so on. Okay, and then it says if n belongs to our integers and n squared is divisible by 4, okay, and we can see that n squared is divisible by 4 in these cases, then n is divisible by 4. Well, what's n? That's n squared. N is 1, 2, 3, 4, 5, and 6. So n is divisible by 4 here, but it's not always divisible by 4. It's not divisible by 4 when you choose 2 or when you choose 6. I'm sure there's plenty others afterwards. But you only need one of those examples. So let's say, for example, n is equal to 2 disproves this one, because when n is equal to 2, n squared is equal to 4. So this is an example of a counterexample which doesn't fit this rule. So the rule doesn't always work. Okay, let's look at the next one. So if n belongs to your integers, then n squared plus 1 is a prime number. And again, all we need is a number to disprove that. But, let's choose 3. So when n is equal to 3, then we have n squared plus 1 is equal to 10. And this is not prime. So there's a counterexample which shows us that the rule doesn't always work. And finally, if it says if an integer is a multiple of 10 and 12, then it is a multiple of 120. Well, multiples of 10, 10, 20, 30, 40, and so on. Multiples of 12, 12 and 24, and until we get to the next 0 is 60 for both of those. So 60 would be an example of a number which is a multiple of 10 and 12, but 60 is not a multiple of 120. So that's our counterexample. We only need one number which is not working to disprove the rule. Right, phew. Okay, well, there's a lot of stuff there, and you may want to go through some of those questions quite carefully again. and some really challenging ideas, I think. But then you have only 10 questions in 1F. So I really recommend that you do all of these questions. So those are the questions in 1F. Obviously, you can work with your book and the answers in the back of the book as well to know that you are right. Okay, after this, next exercise is going to be proof by induction. Thank you for listening in, guys, and good luck with the exercise.